Thank you all so much for being here. It's Tuesday, June 10th at 10:15 a.m. here in Anchorage, Alaska for the 246th meeting of the American Astronomical Society. My name is Kerry Hensley. I'm the Deputy Press Officer for the AAS, and I am assisted today by AAS Media Fellow Lexi Galt, AAS Press Officer Susanna Kohler, who is helping out remotely, and our Astrobytes Media intern Maggie Verico, who will be handling the mic during the Q&A. All of the materials from yesterday's press conferences, the press releases, slides, and briefing videos are all available on the press kit online. So be sure to check there if there's anything you missed yesterday that you want to check out. Today, for this morning's session, there will be 3 press releases distributed. Those will be added to the press kit as well as to the press dash conferences Slack channel on the meeting Slack workspace. So a brief overview of the ground rules in case this is your first ever AAS press conference. If it is, welcome. We're happy to have you here. This is being recorded and we're also streaming live on YouTube. It will be archived there after today. I'm going to give a brief introduction to the topic and introduce our speakers. And after that, we're going to hear from them one after another in the order in which they're sitting. We won't break for any Q&A between the speakers. We'll hold all our questions until the end after we've heard from all of our speakers. So if you're watching on Zoom, you can feel free to go ahead and queue up your questions using the Q&A feature. And if you do that, please be sure to include your name, your affiliation, and who your question is for. And one last note is to please make sure that you've silenced your phone or anything else that might interrupt the briefing. So this morning, we are here in the Planets, Exoplanets, and Brown Dwarfs session, or as it should maybe be called, the Planets, Exoplanets, and perhaps Brown Dwarfs session. We'll hear more about that soon. First, we're going to hear from Christian Soto of the Space Telescope Science Institute on revealing the classical Uranian satellites in ultraviolet. Next up is Emma Dugan from Indiana University on off-polar hint, hottest stars Sub-Saturn Obliquity. Next, we'll have William Balmer from Johns Hopkins University and Mark Giovinazzi from Amherst College speaking on JWST Coronagraphic images of 14 Herc, a cold giant planet in a dynamically hot multi-planet system. And finally, Kielan Hoch from the Space Telescope Science Institute will tell us about detailed JWST observations of a multi-planet system around a sun-like star. All right, with that, I'm going to turn things over to our first speaker. Christian, take it away.
Okay, good morning, everyone. My name is Christian Soto. I am from the Space Telescope Science Institute, and I am very excited to be here to present to you our recent work. I'd like to thank the AAS for this amazing opportunity. This work I've done with Brian Holler, from also the Space Telescope Science Institute, and Richard Cartwright, which is the principal investigator of this whole program. So why do we do this? Well, Uranus is weird, so why not? It's a gas icy giant. It's the 7th planet from the sun. It is tilted about 98 degrees on its axis. It has about 28 regular moons, total moons. 5 of them, which are the regular moons, and they're called the classical. And this is based on the Shakespeare works. The 4 moons on this study are Ariel, Umbriel, Titania, and Oberon, and they're tidally locked to Uranus, so they always show the same side of the planet. Now, this together with the way Uranus is, makes the system very unique because of the planet's obliquity, which results in extreme seasons on the moons. Now, going back to how these moons are tidally locked, that means the moons facing the direction of the motion is called the leading side. Now, the one opposite to that is called the trailing hemisphere. Now, the bombardment of the surfaces of the classical Uranian satellites from charged particles in the planet's magnetosphere, which is highly asymmetric, and also from the galactic cosmic rays, creates CO2, ice, and it might be the cause of the darkening on the trailing hemispheres of these moons. Now, there's always been a high level of uncertainty on how much the magnetic field actually interacts with the satellites. And that's where we come in. That's our main motivation, to study the system and search for signs of interactions between the planet's magnetosphere and the surface of the moons. This is called something that we call radiolysis. So for this, we have an initial hypothesis. And yes, I call it initial because there's a plot twist. But our initial hypothesis, we call this the magnetosphere story. So based on interactions with the planet's magnetosphere, the leading side of these moons should be brighter than the trailing sides. That's due to the radiation darkening of the trailing sides. But what I already mentioned is charged particles that are trapped in the planet's magnetosphere. So more on this. This is an image from Cochrane et al. From 2022. It shows, it illustrates the orientation of the magnetosphere relative to the Uranus moons. Now, the thinking was that the charged particles are trapped along the magnetic field lines, which primarily hit each of the moon's trailing side, which should darken the hemisphere. This means that, the Uranus as a system it's dramatically tipped relative to the orbital plane of the planets. Because of this, and the magnetic field lines rotate faster than its moons orbit the planet, the magnetic field lines constantly sweep past the moons, and that's something important to remember. So the how, we use Hubble data from the STIS instrument on board the Hubble Space Telescope. This is a program from Cycle 29. PI was Richard Cartwright. As I say, we used the STIS instruments, 16 orbits were completed. And like I said earlier, we studied the 4 of the largest moons. So to observe the brightness of the 4 largest Uranian moons, we require the unique capabilities of HST's UV parameters. Now, observing targets in UV light is not possible from the ground because of the filtering effects of the Earth's protected atmosphere. There's no present-day telescope that has comparable UV vision and sharpness. So we use UV spectroscopy data obtained from STIS, like I said earlier, to study the UV darkening of the satellite surfaces and also the potential absorption features from radiolysis. So how do we analyze this? We analyze this data using the Hubble Advanced Spectral Products pipeline. HAS provides high quality one-dimensional spectra of all spectroscopy, most of the spectroscopy data from HST. So that includes the COS instrument and STIS instrument. The pipeline offers robust co-added and combined products for nearly every spectral data from the Hubble's instruments. So we essentially reduce the STIS data to make sure that we understand the data, and it is very weird, and you'll see later on why. Now, this image here shown, it's a resulting plot from one of the moons after it was run through the HAS pipeline, and it's only shown in the one moon, one hemisphere, but it's just a summary. All of them look very similar, just the difference in the flux. So the analysis and the results. So here I'm showing the 4 plots. And so going back, so we analyze the data using the HAS pipeline, right? So we make comparisons between the leading and trailing hemispheres of each of the satellites and also between the satellites. And this was done to evaluate mechanisms responsible for previously observed hemispherical dichotomies. That means contrast between both hemispheres. Now, once we reduce the spectral data for each moon and its hemisphere, that data was divided by the solar spectrum, and then we use the resulting plot to calculate the geometric visible albedos, and that's what you see in these plots. You have on the y-axis, you have the albedos plotted against the wavelength, and you have the four moons. So these results are crucial for understanding the degree of charged particles bombardment on the moons, revealing new insights of the ongoing surface evolution of the Uranian satellites and providing a better understanding of the role that the magnetosphere of the planet plays in the evolution of the surfaces. So we thought, going in, we thought, the leading side has to be brighter, but instead we found evidence that there's no radiation darkening on the moon's trailing sides, and there's clear evidence for darkening on the leading sides of the other moons. So as you can see here, umbral is very similar in brightness when you compare the trailing and the leading hemisphere. Leading is the one in cyan, trailing is the one in magenta. But when you see the other ones like aerial, titanium, especially Oberon, you see a big offset. So instead of the trailings of the instead of the so we see that the three moons show darker and leading hemispheres, which contradicts our initial idea that the trailing hemispheres should be darker. Now, I want to point out for Titania, we think that that one is likely to be next in line to scoop up the dust from irregular satellites that hit after Oberon. So all these brightness differences surprise us, and it indicates that Uranus magnetosphere might not interact with its largest moon. So it contradicts our initial thinking. So what we think is happening is we think that micrometeorites are constantly hitting the surfaces of the Uranus irregular satellites, which ejects more dust, more material as it orbits, it goes into the orbit around the planet. Now, fast forward, many years, scale of millions of years, this dust and material moves inward towards Uranus and eventually crosses the orbits of the other moons. And these moons then sweep through the dust and picked it up primarily on the leading hemispheres. The best analogy that we can come up with is think of you driving very fast on the highway and bugs are hitting your windshield. That's what we're seeing here. So this material causes the moons to have darker and redder leading hemispheres. And this is some of the first evidence that we're seeing of a similar material exchange among Uranian satellites. And this supports our or a different explanation. So we're moving away from the magnetosphere story and we move into what we call the dust transfer story. So based on these findings, we suspect that the magnetosphere is fairly quiescent, so it might be more complicated than we thought. Perhaps interactions between the moons and the magnetosphere are indeed happening, but for some reason they're not causing the asymmetry that we thought. So instead, we think that dust from some of the Uranus irregular satellites is coating the leading sites of the other moons. And this answer will require more further investigation into the enigmatic nature of Uranus, its magnetosphere, and its moons. And I'll leave you all with my conclusion. Our results changes our view of the magnetic environment. It shows how material transfer within the system. And very important to know, we will follow up on these same 4 moons on the trailing hemispheres using James Webb, specifically using a NIRSPEC instrument. And this is a cycle 4. So we will be observing this in August and September and then in January. And that's all. Thank you very much.
All right, good morning, everyone. I'm very pleased to be up here speaking to you today about a result that I have worked on with Songhu Wang and Shenyu Wang at Indiana University in Bloomington. And it is about the off-polar hint of the hottest star Sub-Saturn obliquity measurement. So to start with what I mean by obliquity, I mean the angle between the star's spin axis and the orbital axis. So if we look very close to home in our own solar system, we see that it is very reasonably aligned to within about 7 degrees. So we want to see if this is true for exoplanetary systems as well, or if it differs. And the way we do this is by using what's called the Rossiter-McLaughlin or RM effect. As the star is orbiting, part of it will be orbiting toward or spinning towards us and blue shifting its light, and the other side rotating away from us, red shifting its light. So we combine radial velocity measurements during the planet's transit, and as the planet passes in front of the star, it's gonna either block the blue shifted or the red shifted portion of the star, and that information can tell us how it's orbiting. So if it's only blocking blue shifted light, then it's kind of orbiting perpendicular to the star rather than well aligned, such as we see in the solar system. So Jupiter's have been the easiest to detect with both the transit and radial velocity measurements due to their high masses, especially close in Jupiter's, as they have that higher effect on their star for radial velocity and then also block the largest portion of the light for transit. So we have a large data set for Jupiter's to study this relation. So on this plot, we're looking at the stellar effective temperature and projected spin orbit angle. So the projected obliquity from the sky rather than its true obliquity. So on the x-axis, we can see the stellar temperature, and then there is a dividing line, the dashed line in the middle, which represents the craft break at around 6,100 Kelvin. And this line is of interest because what we can see from studying these Jupiters is that around cool stars, Jupiters tend to always be well aligned. However, around hot stars, they tend to be they have a tendency to be more misaligned rather than just well aligned. So the next question is to look at what do other populations of exoplanets look like? Do they follow the same relation as Jupiter's do? So if we look at sub-Saturns, which we are saying is the mass just below Jupiter, so if we're defining Jupiter's in this work as 0.3 to 10 Jupiter masses, these sub-Saturns are 0.1 to 0.3 Jupiter masses, so a little bit smaller. But what we're seeing is that they can be misaligned around cool stars, right? We have a significantly lower amount of data points for sub-Saturns, yet we're seeing that around cool stars, they are misaligned. And we also find that they fall in a polar orbit region, roughly 60 to 120 degrees, right? Counting for error bars and saying that 90 degrees is a true polar orbit. So what we're seeing with these planets around these cool stars that are misaligned, they also fall into this polar region. And what we would like to do is extend this to hotter stars, because as we see with the Jupiters, we see that they are often misaligned around their hot stars. So we want to extend this for the sub-Saturns as well to see if this is still going to hold true for them as well. Which is where the main subject of our work, TOI 1135, comes in. TOI 1135 orbits a hot star, is a puffy Saturn mass planet, so it has an inflated radius in comparison to its mass. And it's on a close-in orbit on the order of days. And it has a near polar obliquity. So on the plot on the right side of the screen, we see the radial velocity measurements during transit for this system. And we get that it has a sky projected obliquity of negative 62.7 degrees. So it's on the border of that polar obliquity range. So it's very near. But one of the most interesting things about this is that it is the hottest system that we have measured thus far for sub-Saturns. So this is also interesting because what we see is that there is a potential anti-correlation between stellar effective temperature and sky projected obliquity, whereas for the misaligned sub-Saturns, as that temperature gets hotter, we see it lowering. Hopefully this will give us some insights into the different formation mechanisms and how this differs from Jupiter's and sub-Saturns and how those formation and evolution pathways differ and how they are similar. And we can learn more about that formation story as a whole. So I'll leave you with my summary that TOI 1135 is the hottest star with a Rossiter-McLaughlin measurements of a sub-Saturn. Sub-Saturns can be misaligned around cool stars. Generally, sub-Saturns are on polar orbits, and around hotter stars, they start to veer toward that off-polar side of things. Thank you.
Hi, everyone. My name is William. I'm here with Mark, who's going to help me answer some questions if you have them. And I'm excited to talk to you today about our direct image of a cold giant planet in a dynamically hot multi-planet system. As exoplanet astronomers, we're interested in understanding how planetary systems change over time. We want to measure the atmospheres and the orbits of many different planets with different masses, temperatures, and ages especially, in order to place our own solar system and its evolution in a galactic context. We want to understand how these planets change because we want to understand how we got here. One of the best ways to study exoplanets, in my opinion, is by directly imaging them, by resolving their light apart from their bright host stars. But doing this is very technically challenging because planets are like fireflies next to lighthouses. They're thousands, millions, and even billions of times fainter than the stars that they orbit, and they only get colder and fainter as they age. This means that although we can image some of them, the ones that we have imaged tend to be hot, young, and very massive. These planets have told us a lot about how planets form, but not a lot about how they've evolved over time. With JWST, though, we expect to be able to image cold giant planets for the first time. This is because JWST has unique sensitivity in the mid-infrared, where colder planets should be brighter. Nevertheless, as you go to longer wavelengths of light, your resolution necessarily decreases. So we need to find young systems or old systems that are nearby that have planets that orbit far enough away from their stars that they can be resolved. We took a look at the 14 Hercules system, which has a storied history of observations. It's a nearby sun-like star with 2 gas giant planets in orbit around it. You can see the radial velocity monitoring of the system that revealed the 2 giant planets. And importantly, absolute astrometric accelerations from the Hipparcos, Hubble, and Gaia space telescopes appeared to indicate that these 2 planets were on misaligned orbits, vastly unlike our solar system, where all the planets orbit sort of within a pancake. These 2 planets appeared to have undergone a sort of planetary tug of war, where the outer planet was kicked onto a much wider orbit. This is great news, however, for direct imaging, because it means that we could confidently predict that JWST could resolve the outermost planet in the system. And this is our prediction of the location of 14 Hercules C based on the most up-to-date orbit fits before our image. And here is our direct image of the system. This is a 275 Kelvin planet at around an arc second from its star, orbiting with an orbit about 15 astronomical units. Right on target. The planet's actually significantly fainter than what we'd expect based on all those evolutionary models and based on its mass and the system's age. We don't think that this is a problem with the evolutionary models, however. We think that this is because strong updrafts in the planet's atmosphere are bringing hot, opaque gas from its interior up into the outer reaches of the atmosphere. And these, along with maybe some slight icy condensate clouds, are blocking some of the light in the 4 to 5 micron filter that we use to take this picture. This will tend to redirect light to even longer wavelengths. And so in the future, we should be able to study this planet with JWST's other instrument, MIRI, where we could take a look at the ammonia and other cold gases in the atmosphere that we don't have access to on the ground in hotter exoplanet atmospheres. We also took a look at the orbits of the system. We refit the orbits with our new measurement of the outer planet's position, and we confirmed that they are still at odd angles with respect to one another. Secular orbit simulations show that the 2 planets are still in their tug of war. They're exchanging angular momentum back and forth, but that these wobbles appear to be stable over long time scales. So whatever dynamic scattering event happened to kick the outer planet onto its wide orbit has settled into an unhealthy equilibrium. We're trying to understand what kinds of planet-planet scatterings could produce such an exotic configuration of orbit. So that's future work that's going to be led by some dynamicists on our team. In conclusion, I think 14 Her is one of the coldest, oldest, and faintest planets that we've imaged to date. It joins TWA 7b and Epsilon Indi AB in this completely new regime being unlocked by JWST. In the near future, we hope that follow-up studies of these systems will be approved and will reveal a whole lot more about how the atmospheres and dynamics of planets can change over their billion-year lifetimes. I'll leave you with our press release image. Please reach out to Mark and I if you're interested in talking more about all the work that went into this discovery. Thank you especially to the STSCI Office of Public Outreach for their wonderful press release, which you can view online now. And Mark and I want to extend a big warm congratulations to our team lead, Daniela, on the birth of her son, Emilio. Thank you guys so much.
Awesome. Hi, everyone. I am Dr. Kielan Hoch, a Giacconi Fellow at Space Telescope Science Institute, and I am here to talk about two major discoveries in the same planetary system, WISIS-1. But before I go through the results of this research, I really want to highlight the team that did this research. So the first 5 authors of this paper are all early career students, ranging from a first-year grad student all the way to me, a third-year postdoctoral fellow. You can also maybe see a familiar name on the screen. William Balmer also is heavily involved in this program. So to just overview of JWST is that JWST was not made to image planets or brown dwarfs like all of us are doing at this table, or even exoplanets. It was made to look at faint puffy galaxies. But even within the first cycle or 2 of JWST, there were some major discoveries, such as Brittany Miles' discovery of the silicate clouds on the planetary mass companion VHS 1256b. She was an early career researcher at the time. I think she was defending her thesis that summer. It was kind of crazy for her. The next one that I wanted to highlight is JWST Miri actually discovered a circumplanetary disk around a brown dwarf companion to a star led by early career researcher Gabriela Cuneo. So JWST is doing stuff with atmospheres and revealing disks around some of these low mass objects, things we never thought we'd be able to do. So now we're going to go into the system. So the WISIS-1 exoplanetary system was actually really exciting at the time it came out because it came out right before the call for JWST Cycle 1 proposals. So no one had gobbled up the target for any of the GTO programs, and it was a really exciting multi-planet system around a sun-like star. So going through the system, the host star is a sun-like star, so solar type. It's the same mass as our sun, but rather than being 4.6 billion years old, this sun is about 16 million years old, so much younger than our own solar system. It's also about 100 parsecs away, 326 light years away from us. It consists of WISIS-1b, the interior exoplanet. It is 160 times the distance from the Earth to the sun, very farly separated, and it is estimated to be about 14 times the mass of Jupiter. WISIS-1c is even farther away at 320 times the distance of Earth to our sun. So super, super far, and it's only 6 Jupiter masses, or 6 times the mass of Jupiter. And so we found out when we were kind of playing around with how we wanted to use JWST to prove that it could do exoplanet science and take images, just as William said. We found out that with the NIRSPEC instrument, we could get both planets in the same field of view, so essentially 2 for the price of 1. So on the right-hand side, you're going to see what we thought the images would look like. So we have B kind of center, C at the bottom, and that kind of line going through is the light from the host star. So here's the actual data. We did pretty well. B is circled towards the center and C is towards the outer edge. It did hit the edge of the field of view in 2 of the dithers, but that's just due to the uncertainty in the pointing of the instrument. Additionally, in the observations we got with NIRSPEC, which we don't have a chronograph like William was saying, but rather we're taking these images at iterations going through wavelength. So not only do we have one image, we have thousands of images going through at every different wavelength here, which is an integral spectrograph. Additionally, we wanted to use MIRI to look at maybe clouds theorized in that wavelength regime. And you can see B and you can see C right in the slit here. So we're not seeing indirect image or indirect spectra of these objects. Like those are them. They're not very pretty, right? They're little pixels, but those are actual planets outside of our solar system. And so this is the money plot essentially. So these are one wavelength slice, right? Because we have an IFU, and this is the image of the planets. We have not subtracted the starlight at all, so that's why you see those features behind them. And you see the full spectrum for B and the full spectrum for C. And these planets are super, super young. So as they are condensing, they are hot and emitting light. So as the light comes to our telescope, it gets absorbed by the molecules in the atmosphere. So that's why there's little dips and bumps. And we've highlighted here all the different molecules that we've seen so far. So we're going to delve into YSIS-1c first. So we try to fit this silicate feature. So the silicate feature is in 7 to 14 microns. And we actually have seen the silicate feature in brown dwarfs with Spitzer data. So in the left-hand portion of this plot, the top two are actually Spitzer data brown dwarfs with the silicate feature. And then VHS 1256b, which was imaged by JWST, is in blue. And then YSIS-1c is all the way down in green. So you can really see it's red shifted, so shifted towards longer wavelengths compared to the brown dwarfs and the planetary mass companion. And then if you just flip it upwards, you can really start to see the shift in the center panel here. So we can go further and start modeling what these clouds actually look like. So what we did was more of a multidisciplinary approach in doing forward modeling and retrieval modeling. And both of those were not able to fit the feature completely. So we took the forward model and actually changed up the clouds and the cloud composition with Picasso and Virga. And this was actually led by an early career researcher, Melanie Rowland, the second author on the paper. And then when we move over to the other planet, because we were really surprised by both of these results, YSIS-1b is the innermost planet, 14 Jupiter masses, and the spectra here is plotted in black. And so if this object was just a planet orbiting a star, it would be the dotted lines in pink and blue, which are just the retrieval and models of what the atmosphere should look like. You can see here that the black line does not go down and actually kind of stays flat and then goes back up at the end. So this is indicative that there's some sort of black body or some sort of emitting material around the planet that is causing it to stay bright at longer wavelengths. So when we do our forward models and our retrievals, they still don't fit this kind of material around. And it turns out that's because there is another emission portion. So the other emission portion you'll see is in that right panel. So if we subtract out the overall bump, you see another bump from 9 to 11 microns, and that is the first detection of olivine in a circumplanetary disk in this system. And this is kind of strange because these are coming from very, very small grains. And with our current theories, these grains should not still be around at 16 million years. They should be gone around 2 to 5 million years. So this object, we might actually be seeing maybe second generation grains that have been rethermally processed through maybe collisions or formation of a moon. So I'm going to leave up this last slide. So kind of what I was saying before, theories have suggested that brown dwarfs should start to lose their clouds at around 900 Kelvin. But when you look at these directly imaged planets with the direct spectra, you still see evidence for clouds at higher temperatures. So we've thought maybe that these two distinct classes of objects might have different clouds, and this could be the first evidence of that. However, we need to see if this trend will hold and obtain these MIRI data for all of the directly imaged companions and see what happens. And then the CPD around YSIS-1b challenges all of the theories that we have on circumplanetary disk formation and also just planet formation and the time scale. So if we use those time scales, then these have to be second generation grains. But YSIS-1b is not the only object that still has material around it at a much older age, but it is the first one to still have silicate emission. So evidence for collisions or exomoon formation could be possible, or we just got to put in a little bit more work to reveal all the complexities that are happening with what we see with JWST. And another shout out, early career researcher actually helped make this press image, and they are in the audience right now, El Bogot. So none of this research and none of these results would have been possible without early career researchers, highlighting the need to support all of us. Thank you.
All right, it's time for the Q&A portion of this session. So for those of you here in the room, Maggie is going to bring the microphone to you. Please wait for the microphone before you ask your question. And remember to state your name, your affiliation, and who your question is for. Same goes for the folks online. Be sure to include that information in the Q&A box when you ask your question. All right, let's start things off here in the room. Ethan would like to ask a question.
Hi, thank you. I'm Ethan Siegel from Starts with a Bang on Big Think. This question is for Christian. Christian, I want to know, do we have hemispherical maps of these Uranian satellites in either the optical or the infrared in addition to ultraviolet?
That's a good question. We're actually going to follow up with James Webb to get the infrared data. I'm not sure about optical, but I know for near infrared, we are planning to get that within the next year for the same 4 moons on the trailing hemispheres.
Okay, I was a little confused that you showed the individual plots for spectral darkening between the hemispheres, and the moons go in order: Ariel, Miranda, Umbriel, Oberon, Titania. But if I look at the darkening, it looks like Titania is not darkened at all.
Oh, yeah.
Ariel is the second most darkened, even though it's the closest. Oberon is the most darkened, and Umbriel is only a little darkened. Is there any kind of dust model that explains why these planets would experience the darkening they do in the order that you see it?
Not in the order, and that's one of the weird findings that we got, because we were expecting Ariel and Umbriel to be very similar, but Titania and Oberon to have the contrast. And like you say, you actually see that in Oberon, but not Titania. And what we think is that the model that we have is what we call the dust transfer story, right? That we have all these dust from the regular satellites, and it's sweeping past the inner moons, and instead getting to the outer moons, meaning Titania and Oberon. But for some reason, Titania is being saved from that, and Oberon is just getting all of that dust. Maybe with more time, we might see some of that dust making its way to Titania. I do not have the answer for Ariel. Another thing to add to Titania is that maybe what we're seeing is not UV detectable at the moment. So maybe with the near infrared data that we'll get will help us answer that question more. Thank you for your question. Very good.
Thought I saw another hand in here before. All right, over here.
Hi, this is Ariel with Harvard and Sky and Telescope. I had a question for Kielan. I was just curious if there was a measure of the size of the circumplanetary disk, or its total volume or extent, and if not, if that's something you're interested in learning about in the future.
Yeah, so with just the dust emission and black body emission, it's really challenging to get a full size scale for the disk because we're missing the gas portion. So the disk is kind of made up of both dust and gas. And so since we were only really able to constrain the dust portion, we really need an instrument like ALMA, but also JWST MRS data, which actually is going to be observed in cycle 4. That's what just happened, cycle 4. Yeah, okay. And hopefully we'll see some gaseous lines, and we'll be able to expand upon trying to figure out what the size scale of this disk is, because the disk really shouldn't be here right now. So Maybe there's some proof for substructures, moon formation, things like that. But this is all like a brand new field that's starting to reveal with JWST. So stay tuned. Put that over there.
Other questions here in the room? Looks like we have some online we can go to, or Ethan first and then online.
I've got a couple of questions for some of the other panelists. Emma, I have a question for you. I would like to know, I know there are very few sub-Saturns that we found, especially in hot orbits around stars. You found one around the hottest star yet. And I was curious if you saw any evidence, because this is such a large, puffy, low-mass planet, if you saw any evidence for dustiness, a dust tail, or signals of photoevaporation happening from this sub-Saturn world in your observations?
Yeah, thank you for your question. That isn't something that we have looked at yet. We're primarily working with like photometric data, so we're not really seeing anything like that yet, but I think that would be an interesting follow-up observation to do.
And then I have one for Kielan, if that's okay. Kielan, thank you for this. I was very curious. You gave masses for these two exoplanets at great distances. And given the very short amount of time that these planets have been known to exist compared to their very large orbits, I was wondering how these mass estimates were obtained and how robust are they? In particular, for 1B, you gave a mass that's very close to the border between a planet and a brown dwarf. And I was curious how well these planetary masses were known, if at all.
This is a really great question because for wide orbit exoplanets, especially at these distances, their orbits can be upwards of thousands of years. So we can constrain masses of some of these objects with dynamical masses. So that's something that 14 Her, like William presented, as a dynamically constrained mass. Also, Emily Rickman, who's in the room right now, has a whole program looking at brown dwarfs that have these dynamical masses measured. Now, for this system, they are so widely separated and their orbits are so long, it's very challenging to get a dynamical mass for the objects. In particular, for YSIS 1b, though, because there is a circumplanetary disk around it, that further complicates the mass estimate because it's also actively accreting some of that material from its disk. The mass estimates came from models of the atmospheres and of the spectra. So these masses are what we have right now. And there is some work trying to see if maybe we can kind of constrain a dynamical mass with the object. So definitely stay tuned for that. But that's a very, very good question. Thank you.
All right, shall we go to some online questions now?
Sure. So I have a question for Emma from Leo Enright at Irish TV. So how do we get planets with polar orbits in like formation mechanisms? And a follow-up to that, a follow-up question related to that one is, what would Earth's sky look like if we were in a polar orbit, and would we notice a difference?
Yeah, thank you for that question. So to answer the first part, which was how do we get polar orbits? So that is, part of the question that we're trying to answer. There's some leading formation theories about that. And so for Jupiter's, we have more data. So we see things like planet scattering or things like that, like things come in and kind of knock things out of orbit. And then as they, moving closer to their star, they get, sorry, looking for the right words. They kind of get like, they get closer in and they trade between like inclination, eccentricity, the Kozai leadoff cycles. So we kind of are trying to see if that same picture fits for sub-Saturns. And what we found is that fits this formation theory called secular resonance crossing that was proposed by Cristobal Petrovich. And his theory about this is that because around these hot stars, they are rotating faster, so they are kind of dampening the ability for them to get fully to polar orbits. So around cooler stars, we're seeing that because they are not rotating as fast, they allow these planets to tilt so much that they go to a polar orbit. And this second part of what would the sky look like if we were on a polar orbit ourselves is very interesting, and I have not actually thought about before, but my intuition would say that it would not look all that different. It would kind of depend too if the other planets in our solar system were also on polar orbits. Because if they weren't, we would see different pathways for them throughout the sky. But the main difference, I think, would just be the direction that the sun is spinning in relation to our field of view. So, it might affect like scientific data, but I don't think we, with our naked eye, would perceive like a noticeable difference.
I have another online question also for Emma again. This one is from Jean Malone. And this question is asking, are hot Jupiters and hot Saturns based on the size that we get from transits or the mass that we get from RV? And then if that is the case, what would it be helpful to look at inclination versus radii of these planets for the relation that you're looking into?
Yeah, so just to kind of clarify, the question is like what defines a hot Jupiter from like a cold Jupiter or warm Jupiter?
Yeah, is it a mass thing or is it a radius?
Okay, so a hot Jupiter is if it's close in. Right now, the kind of divisor is about 10 days on its orbital period. It can also be defined by A over the stellar radius. So it's more about like distance from star. Same with Sub-Saturns. We don't have a clear divisor yet about if a hot Sub-Saturn is at the same distance of a Jupiter. That's going to require more data points for us to see, but it's more of a distance thing.
Do you want to take one more from online, or can give Emma a break? Okay. I have a question. This is Kerry Hensley from the AAS. This one's for William. So I believe you mentioned that this is one of the coldest and oldest planets that has been directly imaged. And it seems like JWST has been helping to break a lot of records along those lines. And I'm curious where the record breaking is going to stop. What's the limit with either, make it stop. What's the limit with either JWST or any other facility at the moment?
That is a great question. So I don't think it'll stop at 300 Kelvin, sort of, where 14 Her and these other new discoveries. I think that's sort of the low-hanging fruit in this case. I think, so in cycle 4, I have a program to try and image a 200 Kelvin planet, so stepping down about 100 Kelvin in temperature. That'll be a challenge. I'm not as confident in that program as I was in 14 Her. Don't tell the tech that, but. And there are projects, with even more sort of exotic techniques, like trying to misuse Kielan spectrograph to cross-correlate and discover planets that are around 150 Kelvin. So, I think we're really trying to really find the limits in the next few cycles. I think, by cycle 10, we'll have an idea of where we can make it stop. But I think right now it's anyone's guess.
That's great. Thank you. We can take questions here in the room. Yeah, we've got one here in the middle row.
Hi, thank you. Ellis Bogat from the University of Maryland in College Park. I also have a question for William, because it is really impressive to me how well you were able to constrain where you thought 14 Her-C would show up, and that it was exactly there. I know there's a combination of RV and astrometry data. Are there a number of other planetary systems that we might be able to do this for? Are there any other systems you plan on looking at with as much confidence as we had with 14 Hershey.
Yeah, I think that for 14 Hershey, for having that really clear prediction that panned out so well, it really is the astrometric surveys. So starting with the Parcos, then the Hubble Fine Guidance Sensor, and especially Gaia being able to nail down the positions of these stars, where they are in the sky with relation to one another, so that you can pick out these very, very small tugs that the planets are giving. That gives us, with the addition of the radial velocity, the full 3D orbit of the planet. And there are other stars like this. Like I said, there's a cycle 2, there's a few cycle 2, 3, and 4 programs. I'm leading one where we have effectively the same level of, confidence in where the planet should be. I think, it's a matter of, are the planets going to be as bright, and in what filters, and where can we predict that they'll be the easiest to see in wavelength space? That's going to be the challenge.
Let's take one more from online. Thanks.
Yep, we have one more for Emma online from Bill Waller at the Galactic Inquirer. Is your obliquity referring to the planet's spin orbit angle or the star spin versus the planet's orbit?
Oh yeah, that's a good question, because obliquity can mean a few different things in astronomy. So for this work specifically, it is the angle between the star's spin axis and the orbital axis. So there's the other definition of like how the planet is inclined, but we're talking more about the angle between the star and the planet's orbit.
All right, I've got a question. This one's for Christian. So it's wonderful to be able to make these kinds of observations of moons in our solar system with Hubble and JWST. But what is potentially more exciting is if we could have a mission dedicated to Uranus, which is long overdue. So in a hypothetical, very hypothetical, unfortunately, future in which we have a dedicated Uranus mission, what kind of data would you be looking for to inform your studies of planet magnetosphere interactions?
Yeah, that's a very good question. And I know my PI Richard is he's strong on this idea. We definitely need a mission dedicated to Uranus. I cannot answer what we will get, but I am assuming, like any other science we do in the field, we want to complete the picture, right? So if we have UV, let's do the other wavelengths. That's my intuition right now. But yeah, I absolutely agree. We definitely need a mission to Uranus. So I don't have the complete answer, but I agree with you. We need one. And one thing to point to, going back to what we use Hubble's UV capabilities. We couldn't observe Miranda because it's too close and faint to the planet. But that's when HWO will come in very handy. So
Yeah, great. Well, I hope we get to see a future Uranus mission someday.
That's what we're hoping we get out of all this, different projects. It's just part of the bigger puzzle, and eventually this will lead to strengthen that idea that we do need a mission dedicated to Uranus.
Definitely.
It's very weird, so why not?
Yeah, exactly. Further questions here in the room? I do have one more if you want to continue thinking. All right, Ethan?
This is a very simple question. Christian, I liked your presentation. I saw your release. I don't see a link to a paper. Is there a possibility I could get a copy of that scientific paper that has the figures like the spectra in it?
We don't have a paper yet, but our PI, Richard Cartwright, will work on one soon. We don't have a paper yet.
Okay. Thank you.
But good question, though. Thank you.
All right, I do have one last question for Kielan, and I apologize. This is a little outside of what you talked about. It looked like the orbital distances of the two planets in the system were quite close to being integer multiples of one another. Is that correct? 160 and 320 AU?
Could be.
Okay. All right. This will be a fun question then. I'm just curious, given that, have there been any dynamical modeling studies of this system to see if this is in resonance and if there are other potential planets in the system creating a resonant chain?
So that's a really interesting question. So we have done some dynamical modeling to make sure that the planets are constrained and orbiting the system. As to whether or not there are other planets in the system, that is an excellent question. So the star is super, super young, and I have thought about whether or not there would be close-in planets or companions, maybe tugging on it and looking at radial velocity, or even looking at the star for transits. But so far, any test data is kind of messy because it's a young star, and I haven't really thought too much about trying to do the transit method to tell if there's any other planets in there. But I feel like there should be, because it's weird that you have these two massive planets that look very different than brown dwarfs. So conceivably, they did form in a protoplanetary disk and get kicked out somehow. So what kicked them out? Not sure. So that's definitely stuff that we were thinking about. The system is a huge mystery and just keeps on adding more and more questions to what we believe planet formation looks like.
Great, thank you. Looks like there's lots of weird stuff here that needs to be studied further, which is awesome.
Yep.
Last call for questions online or in the room. If not, we can finish up there. So huge thank you to our presenters for sharing their science, to the PIOs who helped to prepare press releases, and to all of you for being here and for your attendance and your questions. We'll be back here this afternoon for new views and insights into the sun and its surroundings. That will be at 2:15 p.m. and that's featuring first light observations from Punch and Codex. So you'll definitely want to be here for that, as well as our other presentations. And finally, let's give one last round of applause to our speakers.